You already heard about the ISO center. So the ISO center is, in our case, automatically defined. In practice, it can be a little bit more challenging. Yes?
Do you have a question from the on-site participant?
Yes. So it looks like I have this standalone version. So some of the options are grayed out. And is that enough for today's?
Yes.
Okay, thank you.
Yeah. So you have basically the ISO center here. You can set the number of fractions for your treatment. You've also already learned that people come multiple days for a treatment, and like some other stuff here will become clear later on. This will also fill up as soon as we have a patient or some form of phantom loaded. You have some sections here to steer the visualization. Some buttons that are particularly interesting are here. This one, which helps you to visualize your angles, the visualize plan beam button down here. Of course, also showing the dose volume histogram is something that we do a lot in treatment planning. And also like the 3D view, I think it's written in the workflow and you can click it, but MATLAB is not very efficient in computing 3D renderings. So this might take a bit. So it doesn't take 2 hours, but it takes maybe a minute. So you might get stuck if you click this too euphorically. I know that users often like see all these options and they like them. And sometimes just be aware that most of you will not be using high-powered workstations, but you're using a laptop. Like nobody would create a treatment plan in clinical practice on a laptop with like a few gigabytes of RAM and a not so fast processor. So if you have the option to stress your system by changing some numbers, I would not advise of doing it. Good. Here we will later see the patient and we'll have some other visualization things. So there's a lot of stuff grayed out. There's also kind of, I think in the particle therapy masterclass, we sometimes use an educational version because sometimes we have school children and then we gray out some other areas as well. So depending on which standalone you have, there might be even more stuff grayed out, but that's fully okay. Like all the workflows we can do should be feasible. So within matRad, we have a few phantoms and patients ourselves that we can use today. So we do not need to load any DICOM. It's not like bring your own patient day. So we have some data for you to use. The data that we have are either phantoms or scans from volunteers. So this is basically for an open source software. It gets regulatorily a little bit stressful to have like kind of actual sick patients and not some scanned volunteers here. So the data set was created by a few colleagues in the field to really have volunteers with segmentations where at the time when it was created, it was regulatorily very easily to distribute this. So that's kind of the background of the data. So this pre-calculated data is depending on which version you use at different points in your system. And I can show it for Windows, so you click on this load mat data button here with kind of, you can load these MATLAB mat files. And it will query you to look for the data. If you have the source code, so this is only for those who have the source code, your data is actually in the Phantoms folder. So if you go into the Phantoms folder, you will find 5 patients there. A box phantom, which is really just a cubic water box with cubic target. You have a head and neck patient. So if you really want to do some complicated organ at risk management, that's the way to do it. You have a liver patient. You have a prostate patient. And you have the TG119 phantom. If you are a clinical medical physicist, you might have heard of that. It's kind of a typical commissioning phantom from the double APM task report, task group 119. 119, which basically for IMRT created these C-shaped phantoms where you have this C-shaped target, because that's like a standard thing that you can only do with this intensity modulation beam-led approach and not with the conformal approach. If you have the standalone, like I can show you what it usually does when you load it. We try to get around it, and just in the new version we have found a way to do it, but it usually points you on Windows to like some system 32 folder and in a weird position. But it's actually where you installed it. So you basically, for example, on your system, this might be called program files. Since Windows 10, these names are dynamic. You go to in the program files folder, or programs, or however it's called. You go to matRad. This is like the standard installation folder. If you chose a different one, it's not there. I think on Mac, it's also in the application folder where you installed, like if you go into the application folder. On Linux, like it's everywhere, basically, it's in the installation folder. In this installation folder, there's an application folder. And in this one, you have phantoms. It's a little bit difficult. If it is too difficult to locate them, there's a workaround. And this workaround is just, I show this very quickly, to go to our GitHub. Yeah. So basically, this is the code. It's the same link kind of here where we had the release, right? This is the link that you find in the agenda or kind of on this workshop website. And if you just click on code from there, up here, you can basically navigate to the phantoms folder there yourself and just download the patients yourself, and then you can put them wherever you want. It's just a little bit stupid. We were a little bit limited with the installation location of the data when creating these standalone executables. But okay, so the one we start with is actually this TG119 phantom, exactly the one I showed you before. So you can just load it and it will show up on screen, and the user interface will unlock some additional options. So now with just the image loaded, you can just check, yeah, okay, I have my body contour. You see it here on the right, it's named body. In this widget here, you can kind of turn a segmentation on or off. Yep, that's okay. So you see also here the Hounsfield units from -1000 to the window goes up to 1000. So Hounsfield units, I don't know if everybody knows it, but like just a quick reminder, these are units relative to water. Kind of some interesting side note, these units of -1000 on whatsoever, the historic reason is that you basically floating point numbers were a little bit more difficult to use when the CT was invented. So kind of also to store values, you often used integers. And so kind of this is a scale that was built as numbers, as whole numbers from -1000, -1999, and so on, where -1000 is air or vacuum. I have to be entirely sure. I think -1000 depends in exactly the normalization scale, but it should be air, 0 is water, and of course then higher numbers are bones. But in principle, like that's why the scale is so weird from -1000 to whatsoever. And usually you have kind of a range of 4096 values or something like that. And that triggers again something for the people knowledgeable in computers. In principle, you can change such windows here. So for example, you could go to like a more soft tissue centric visualization window, then the table vanishes because it has too high values. And kind of you see there's probably a little bit of scanning artifacts in the water. And one interesting thing about this phantom is also we can, in this widget here on the left, also look at different planes. So not only the actual plane, that's basically a cut like a horizontal cut to the patient's body. You can also look at other cuts. So you see that there's basically a hole in this phantom. And this is also like sense and quality assurance, right? I could take an ionization chamber or whatsoever, put it in there and irradiate it and measure the dose and compare it to the dose that my treatment planning system gives. Yeah. So that's kind of why this makes sense. So you can play a little bit around with the views here. I give you a little bit of time to figure this out. You can, for example, stop plotting contours at all. These big X that you see, X marks the spot, is the isocenter. Like we heard before that basically you need to kind of define your origin and the isocenter. The isocenter is kind of the point of reference for your linac in a sense. It's where kind of the rotation points to. Yeah, so everything rotates around the isocenter. Also for protons and ions, if you have a gantry, you rotate around this isocenter. If you have laser markers in the room, they will mark this isocenter. So this is basically a very, very important point of reference. In the system, this is just now automatically chosen to be in the center of the target. That means when you position the patient accordingly, like kind of, you need to make sure through all the markings that you do initial positioning that like this isocenter is kind of reproducible and your patient positioned relative to the accelerator is exactly like your computer, like your treatment planning system puts this isocenter. That's like something that I basically never care about because I just do research in the software. But if you like, it's super integral that this isocenter is at the correct position in the patient during positioning. Really big part of setting up the patient. Okay, so you see that this is automatically set. These coordinates are relative to the image. So we see somewhere here, it's like at 251 millimeters. Yeah, in X, 326, at 236 in Y and some value in Z. This X is an X when we are in the plane of the isocenter, but we could also scroll out. So if you use the mouse wheel, if you have a separate mouse or like use 2 fingers on the touchpad or however it works on your laptop, you can kind of scroll through. You see this patient is kind of boring. It has always the same, but you see that the isocenter marker switches from an X to pointing either downwards or upwards in the direction where the isocenter is. Okay. Yeah, so this patient is boring, very symmetric, has very few organs and a giant like tumor in relation. But that's a good thing to start with, so we are not overwhelmed with what we are planning. I just changed my view a little bit to this again. Okay, so now, like we are somebody, like I said, we are the engineer that got like a little bit this system and got a collimator and a photon beam to play with. So that's the first thing we will look at. We will create a simple photon beam. We already have the capability to optimize now, so we are a little bit more resourceful than the initial engineer I had or the initial clinical medical physicist. We could now come to the clinical medical physicist who gets all of these things provided. So, and they just want to start, okay, how does this photon beam look like? Maybe they also just want to have a photon irradiation for quality assurance. So they already went to the data loading step, loaded their phantom, and then they set some parameters. So by standard, matRad will give you a gantry angle and a couch angle. Yeah, if you have an educational version of matRad, the couch angle might be grayed out because couches are a little bit difficult sometimes to think about. And if both angles combine, it's like gets a little bit weird if you don't have more things and more sophisticated views to look at. Sorry. But in principle, you can rotate the gantry around the patient, or you can rotate the couch on which the patient lies. I actually can show you, I don't know, we probably saw something like that, but also for the people interested, in matRad, I can show you a bit how this looks like. I just need to find where it is. Technical documentation. So kind of in a very simplified way, that's kind of how it looks like. So you have a gantry that can rotate around the patient. It's also here interesting for you if you want to know what the X, Y, and Z coordinate mean in matRad for you. So X is kind of from the right side to the patient to the left. I will not use the medical terms because I'm not super familiar. I don't know if everybody knows it. Then you have basically the Z coordinate, which goes from the feet to the head. And you have the Y coordinate, which basically comes from top to bottom. So this means that a gantry angle 0 means it's basically just the Y axis, and otherwise it rotates around the Z axis. So that's kind of the linear accelerator head. And you could also rotate the couch, and that's again like the mathematician thinking about the rotation. Yeah. Actually, there would be a Linux, so you couldn't do a 360 on the table. Like that's unfortunately not possible, but you can rotate it a bit in this directions, and you can do both at once. So that's how the rotation works. All right. And we will work with gantry angles today. So just that you know. And you can visualize this here by this visualize plan beams button, like here. So where you see this, very nicely clear that we go down the y-axis in a 0-degree angle. So we go from top into this phantom. And okay, what do we do now? We have selected our beam. There are some other parameters. As said, the radiation mode stays to photons and machine. We have a number of fractions. We will keep the fractions untouched. The nice thing about fractions is basically if you have 30 fractions and you have 60 gray, will be 2 gray per fractions, but relatively all of these things, except from biological considerations, which we can discuss later, from just visualizing it, it doesn't play a role at the moment. Yeah, there are biological considerations to fractionations, but in our case, for now, like having a different number of fractions just means that the dose per fraction changes or whatsoever, and relatively that for visualization and understanding reasons of how the dose looks like is not so important. But we can discuss this later a little bit more. We have some other settings here. And I think in the workflow that you have maybe on the site and this PDF, it doesn't say that we directly do this. But what you can do in this workflow is that you can click run sequencing, because then I can show you the MLC shape as well, even if it's kind of trivial for the first example. No, it's not that trivial. But, and if you like sequencing mean, we create a plan and then we also already compute the multi-leaf collimator segments, like the settings of the multi-leaf collimator to calculate or to basically tell the machine how it should configure the irradiation. So this run sequencing, you can basically give the sequencer a number of levels or number of intensity levels it can use to create the fluence. I will explain this in a while. So these are kind of settings. There is one setting here which we call the pixel width that tells you how big you want to choose your small beamlets. Please do not change this too much. Like kind of, let's say you have a 50 by 50 field. Yeah, like that's too large. Let's take a 10 by 10 centimeter field. Yeah. So what this setting does, it basically creates 5 millimeter wide pixels in this field, 5 times 5 millimeters. If you make this smaller, then the number of beamlets increases quadratically with this. Yeah. This might not seem important or whatsoever, but if you need to compute 100 instead of 10 beams, it's just stress for your computer and it takes time. So if you make this smaller, it's very likely that you will run out of memory. If you make this higher, it's very likely that your plan quality suffers. So this is already something that kind of these parameters, and here's also the computational bottleneck of treatment planning a bit. You can create, in principle, super accurate representations of these discretized fluents, but then it's just too heavy to compute. Yeah, like also in particles, you could put in 1 million kind of distinct spots, but then you need to compute 1 million distinct proton doses, and it will take ages. So there's a trade-off with the involvement of computers and stuff that you can actually use for treatment. That's also, for example, why VMAT came a little bit later than these segmented treatment, because you need to compute a lot of intermediate beams for VMAT, and you just need computers to catch up with what you want to do in a sense. Yeah, so put it to 5. Of course, there's also the limitation of how big your collimator leaves are. Doesn't make sense if your collimator leaves are 5 millimeter equivalent size to create beamlets that are 1 millimeter small if you cannot even physically create these sized beamlets. Yeah, then the sequencing algorithm would need to change this anyways. So let's stick with this. Usually 5 millimeter works. If you really realize my computer is so slow, you could also consider like increasing this a little bit, then you get less beamlets and faster results. So that's kind of the setting. And now, like, we go to the computation steps. So first, we compute the dose for each of these beamlets. And we can do this by clicking this, in general, by just clicking this calc influence matrix button. It creates a dose influence matrix, which meaning the dose, like the influence of the dose, like kind of is the thinking. So which influence on the dose has every individual beamlet? So we can calculate it, and it will be reasonably fast. So I have this laptop, which is quite fast. Your laptops might, some of you might even be faster. Some of them might be a little bit slower, but it takes a bit. Like in the background, usually matRad configures the resolution a little bit lower and so on, so that it doesn't take too long. But nothing happens yet, because we do not really have a dose yet. We know the dose of each individual beamlet, but we do not know how intense the dose of every individual beamlet should be applied. As an intermediate step, I now quickly go into the background of what happens, because I don't know how many people are interested a little bit in mathematics or physics, computational stuff like coding, like a little bit. One person with online might be a little bit more. So in the background, like just to show you this, like we created a lot of logic to enable this. And the nice thing about matRad is you can directly look at this. If you have the source code installed, it doesn't work with the standalone. You need the MATLAB environment and really look at what actually happened. Yeah, so there's like this one data structure that we call STF. Yeah, this basically stores the geometry. And it tells us, for example, that we created 313 beamlets for one beam. Yeah, and this is basically in matRad, we call those beamlets rays for photons. And it also tells us that these rays have certain positions, and you see that they are all spaced 5 millimeters apart. Makes sense? We saw this. Like if you have the standalone, you cannot look at this. That's why I'm showing it for the people who are just using the standalone now. So it kind of makes sense. The whole geometry is now generated for one beam, stored here. And now for the mathematical interested people, we also, that our dose that we calculated is stored in another data structure and is really just a matrix. Yeah, it's a matrix that has columns. Like each individual beamlet basically is a column in this matrix telling us where to put what the dose in the voxel of the CT of this patient is. So basically this number here are all relevant voxels in the patient. These are indexed, like row 0 would be the first voxel, row 1 would be the second, and so on and so on. And just like for the mathematically interested people, why is this a matrix? Because now I can do some really nice thing. I can just do a matrix vector product with any vector I want. And this will always give me, oops, sorry, I have like out, unfortunately. This is a matrix vector product which creates a dose. Yeah. So mathematically, that's very important. And I can guarantee you that every treatment planning system has this object, maybe not exactly like we store it. Maybe it might be separated by beams or it might be separated by organ, but they use this object because you can calculate the dose for an arbitrary modulated beam just by multiplying with a vector. Just for the mathematically interested people. Okay, so this object now lives in our background. It doesn't tell us something about dose, but for that we have asked the operations research engineer to build us an optimizer, and you can click on optimize. This is usually the step where we get like 1 or 2 complaints that it doesn't work because there might be an incompatibility between the new M123 Max and the old MATLAB, which was still compiled for Intel Max. So this is sometimes one thing, but usually this basically opens a window here that minimizes a function. So you see what this algorithm actually does. It kind of sometimes also needs to wait a bit for the results. So at the moment, yeah, there might basically in the background, there might pop up a dialog depending on how large your screen is, that you need to click OK on. But what you see, this is exactly like calculating a function from a starting point and making this function smaller. With one beam, there's not much to optimize. You cannot do much with one photon beam. But our optimizer will already try to kind of reduce the dose in the organ at risk, while trying to increase the dose in regions which do not pass through the organ at risk. It's the only thing the optimizer can do with this single beam, right? It doesn't have any options to distribute or accumulate dose in the target. It will just try to somewhat increase dose in the regions where we do not pass through the organs at risk. And you will have insanely high doses here just to get to the prescribed dose in the target. Yeah. Basically, there's not much to do in this case. And then the treatment planning system will ask the leaf sequencer to create kind of the multi-leaf collimator shapes for this beam. Yeah? Because as said, we do not configure the collimator to create the tiny beamlets step by step, but we basically do what you do when you go to Photoshop and say, okay, I have an image with 16 million colors, yeah? But I now want to discretize this only in 6 color levels. And then you get like some interesting looking, artsy looking color levels for your image. And that's kind of the same thing that the sequencing algorithm does. It basically says, okay, I have this continuous fluence map, like this continuous modulation in a sense, like continuous values that my optimizer found out. And I just create a number of levels, which I stack on top of each other, one after the other. So I rotate my beam to 0 degrees. And first I irradiate this collimator setting. Then I irradiate this collimator opening. Then I irradiate this. And when I stack them all on top of each other, I get a beam that looks like this. Okay? So that's what's happening. You calculate these beamlets, you create values for each of these beamlets of how intense they are, and then you do a sequencing to create these collimator shapes. Good. So, but how did we actually end up with our beam? How did the optimizer make this choice? And these are where the functions come in, right? We had these functions decided upon. One quick question from the schedule: when are we going for the lunch break?
In 25 minutes at 1.
At 1, perfect. That's very good timing, actually. Really nice. So basically, how did the optimizer end up with this decision? So in this one beam here that you have opened, it could also have decided to allow you not to go so high for these in these regions. So if you look at the units, these are basically here. I can look at it. It's 2.3 gray per fraction. While in the tumor here, we have only 1.7 gray per fraction. So we could also have not allowed it to go as high like this. It could have stayed lower. And this is where the whole prescription and these mathematical functions come in. So you see on the left side here, in these objectives and constraints widget, you see that there's a few functions lined up. You see basically there is our target. It is designated as the void type target. It has a priority of 1. It's called the overlap priority. It means this is used for managing overlap. So basically it says that, like, if a lot of people often do some stuff in Photoshop or stuff like that. So it's like when you have multiple layers in Photoshop, right? A higher layer, or in this case, a lower number overlaps a higher number. So it means, for example, the target overlaps the body. If I would say the body would overlap the target, basically the target would not be seen because it would be hidden behind all the voxels in the body. So the target has the highest, like it's on number 1 of our priority list. Then comes the organ at risk, and then comes the body. So then you have a function, and these functions in clinical treatment planning systems, they are usually nicer named, but less descriptive, or like a little bit, I would say sometimes they say something that is not entirely true. For example, in a clinical treatment planning system, you might call some function a minimum dose, but it does not guarantee you to reach the minimum dose and stuff like that. And it has a different formulation. So, but in this context, for example, the function is called squared deviation, and it quite literally measures the quadratic difference to a prescribed dose. The prescribed dose, or the dose parameters in general, are here on the right, where you have parameters. So for example, here it is a reference parameter of 50 gray. That means you want 50 gray in 30 fractions, which means you want to have kind of 1.66666, like 1 to 1.2 thirds, 1/2 thirds gray per fraction. You could, for example, change this to 60. And if you change this to 60, then it would become a little bit easier because you now would look for 2 grays per fraction. matRad would always output gray per fraction. It has a little bit of reasons related to ion therapy, where you have these biological models which have a non-linear dose relationship to response. And then you cannot kind of normalize that easily. So you always need to do a little bit of thinking in your head. And I like it in educational things, especially when you have school children, because that's something that they can a little bit, if they are in higher school, calculate in their head directly, and then they're happy that they can calculate something. But this means that it's kind of like 60 gray in 30 fractions. The standard setting is 50 gray for some reason in the data. So this would end up with 50 gray in 30 fractions. Then we have in the other organs, we have squared overdosing, which means we measure only the quadratic term of positive differences. If the difference is negative, then we don't say it's basically, we throw it away, 0. But when it's a positive difference, the value is higher than the reference dose, it contributes to our function. This makes it easy, for example, for organs to pull dose down, and as soon as you are below that level, you're fine. It doesn't make sense to use a squared deviation on an organ, because that would mean you would try also to pull the dose up. You don't want to put dose in an organ unnecessarily. So these squared overdosing functions kind of pull the dose down. And if you are below that level, they are fine. And what you could then, for example, see in treatment planning, that you have like multiple of these squared overdosing functions, or maximum dose functions sometimes called. Like one for a very high level, yeah, that is very important, and one for a lower level.